And so you don't see anything. It's black. But does that mean there's nothing there? No. There's a lot there. You just can't see it. Okay? So this background radiation was serendipitously discovered by Penzias and Wilson. They wrote this paper in 1965, which is it's about 1.5 pages long. I always kind of tell my students that it doesn't take much to win a Nobel Prize. The paper was only a page and a half. And it's almost an apology. When you read it, they didn't really know what they had discovered, but they had discovered something, and they talked to some colleagues, and they said, "Oh, I think you've discovered this background radiation. This signal here, you found it." They were looking for something else, but they stumbled upon this. So they used this reflector antenna in New Jersey, of all places, and they detected the signal. And therefore, in 1978, they won the Nobel Prize for this discovery. The picture of the sky, so this is the picture of the very early universe that they essentially took, looked like this. Not particularly interesting, right? It's just an orange blob. And that's because with the sensitivity of the instrument that they had at the time, they pointed in any direction and they found they found this 3 Kelvin body, and that was basically it. There was no real structure. So that led to follow-up observations. So the COBE satellite, shown here, made a measurement of the microwave background as well, follow-up measurement, and which led to another Nobel Prize in 2006. So what they found is the very nice black body spectrum. They measured this from space. So that was great. It looks a little different than the plot that I showed you earlier, but that's just because of how it was plotted. And the other thing that's interesting to note is this is the actual data. It's not just a theoretical model, so they really nailed it. They also measured that instead of the orange blob that I showed you, they measured that it actually looks more like this. So the temperature is spatially varying. If I point to one point in the sky, the temperature is 3 Kelvin plus a little bit. If I point to some other point on the sky, the temperature is a little bit different. So they discovered this anisotropy. Temperature anisotropy. It's very small. So here's a black body curve plotted for essentially the range of temperatures if you looked at the whole sky. And you can see it looks like there's just one curve plotted, but if you zoom in on this point right here, you can see there's actually 3 curves plotted. So although the temperature varies across the sky, it's pretty consistent. So this is actually important because the anisotropy is coming from in the very early universe when we had this plasma. The plasma is moving around. There's some physics going on that's driving the plasma, and it's sort of alive. And that's encoded in the temperature of the CMB. I'm going to get to that in more detail in just a second. There have now been 3 generations of satellites that have looked at the microwave background. First COBE, the second is Wmap, and more recently Plonk. The main difference here is sensitivity and angular resolution. So COBE started out with an angular resolution that looks sort of like this. So they could see something, but not that much. So Wmap did a follow-up measurement that made an improvement, and Plonk made an improvement upon that. Okay, so here's the, I think this is sort of dramatic, but this is the original COBE image. And then you can see the follow-up Wmap image. So they really are seeing the same thing, but with higher resolution. And so you can see more clumpiness, right? So Plonk said, let's do another measurement, and we'll make another improvement. And their image made it to the front cover of the front page of the New York Times. This is in 2013, so this is fairly new. And this is sort of our best picture of the infant universe now. So as you go to various points on the sky, the temperature is changing. What this picture is telling you is that the temperature is changing by a very, very, very small amount. Okay, so you might say that's neat, but why do you care? What can you actually do with this image? It turns out that there's quite a bit you can do with the image. If you analyze the image and compute what's called the angular power spectrum, which I won't get into, but this is an angular power spectrum here. This is essentially brightness on this axis, and this is angular scale or inverse angular scale on this axis. What you can compute is, imagine that the universe is this plasma, and I do some plasma dynamics. I do some plasma physics calculations, right? But I sprinkle in all kinds of ingredients. I take baryonic matter, which is the matter that we're familiar with, protons and electrons and things that we can touch on Earth. But let's put in other exotic ingredients too, like cold dark matter or dark energy. Right? Things that we don't really understand, but we can include in the model, and we have theories for how they should behave, and so we can include them into the story and see, let's rule them out, right? Let's take all the strange things, put it in the model, and then show that the strange things don't exist, right? So here are some data points. Okay, and then these are 3 different models. So you can run a computer code that will compute an angular power spectrum for you, given the ingredients that you put in. And so you can see, this isn't a rigorous fit, but it's a sort of a by-eye fit. You can see of the 3 models here, the red one looks pretty close, right? These are measurements, and this is a theoretical description of what you think is going on. The blue seems to fail pretty terribly, and the green is even worse, right? So the red model seems right? So now let's see what ingredients do we put into the red model. The red model is model number 1, which is down here. These omega parameters tell us something about the energy content of the universe. So for the red model to be correct, 5% of the universe is baryonic matter that we're familiar with. 25% is some cold dark matter, which is matter that you can't see, but it gravitationally is out there, and it's impacting things like galaxy dynamics. But we can't see it with our eyes. We can't see it with photons, with light. We can only see it through gravity. And 70% of the universe is dark energy. And what's dark energy? Nobody knows. Okay? But you can include it in a cosmological model as an energy density. You can just say, the universe has some background energy density. I'll put it in the model and let's see what happens. It turns out that the best fit model to the data includes the predominantly dark energy in the universe. So what are the failure models here? Let's take a look at those. Model 2 is not so great. Model 2 has 5% baryons and 25%